Hello everyone, my name is Xuning Hu, and I'm a final year undergraduate student at Xi'an Jiaotong Liverpool University. It's a real honor to present our work, exploring and modeling the effects of eye tracking accuracy and precision on gate-based steering in virtual environments. This research was carried out under the supervision of Professor Wolfgang Studerlinger and Professor Haining Liang. Let me first introduce what we mean by a steering task. Steering is about navigating from a starting point to an end point along a constrained path. It is a fundamental interaction task in HCI, and is also very common in our daily life, such as in cascading menus, driving, gaming, and so on. To avoid poor interaction experience, phase law was first proposed. It models target selection time based on the size and distance of the target, and is often seen as the golden rule for pointing task. Extending this idea, Account and Jai introduced a steering law, which predicts navigation time along a constrained path through path integration. They validated it within many different input devices: mouse, pen, trackball, and even the track point. Later, Yamanaka examined the law in driving task and refined the model for that context. And more recently, we tested it in freehand and controller-based interaction, further adapting the model to these modalities. From this, we can see that whenever the input modality changes, the characteristic of steering task must be re-examined and validated. Gate input is becoming increasingly common and is now adopted as a mainstream interaction modality in high-side, such as the Meta Quest Pro and the Apple Vision Pro. However, we still don't fully understand how gate input affects continuous steering task. In addition, gate is a very special input modality, with a unique characteristic such as inherent microscars and the insensitivity to distance. At the same time, it is also strongly influenced by eye tracking quality, which introduced further limitations. Here, I show some data reported by major high-side manufacturers on gate quality under the best lab conditions. Even in these best case setups, there is still considerable error. And in more realistic settings, such as when user move or when lighting conditions change, these errors can become even worse. This shows that eye tracking quality is something we cannot ignore when designing or evaluating interaction tasks. Therefore, in our study, we focused on the characteristic of gates and the errors introduced by eye tracking, and how these factors affect performance in steering tasks. Based on the motivation, we set out 4 research questions. Research question 1, how do past features such as width and length influence user behavior in gate-based steering tasks? Research question 2, how do spatial position and accuracy of eye tracking influence user behavior in gate-based steering tasks? Research question 3, how does user behavior in gate-based cursor control align with the steering law? Research question 4, can the effects of spatial accuracy and precision on user behavior in steering tasks be captured or explained through mathematical modeling? In general, gate quality is described by 4 parameters: spatial accuracy, spatial precision, sample rate, and data loss. But with improvements in computing performance, both sample rate and data loss have become relatively stable. So in our study, we focus mainly on spatial accuracy and spatial precision. Spatial accuracy means the offset between the actual mean gate point and the cursor. Spatial precision describes the separate of gate points, essentially the level of jitter. To simulate degraded eye tracking quality, we added a fixed offset to reduce accuracy and applied white Gaussian noise to reduce precision. The formulas and corresponding visualizations of these manipulations in the steering task are shown here. Therefore, we designed a within-subject experiment based on parallel work on task difficulty. We selected 2 path lengths and 3 pathways. And from the eye tracking quality parameters we just discussed, where accuracy error is often about twice as large as precision error, we designed 3 levels of accuracy and 3 levels of precision to reflect realistic conditions. Here is a short video demonstration. This one shows an accuracy error, a fixed offset. This one shows a precision error, white Gaussian noise. And this one shows both accuracy and precision errors combined. We also recruited 24 participants and recorded their familiarity with VR and with gate interaction. The study we conducted on the Quest Pro high side using its built-in eye tracking system. Before starting, participants adjust their IPD, completed the built-in calibration, and then verified by themselves whether the gaze cursor correctly followed their eye movement. As I mentioned earlier, we simulated degraded eye tracking quality by artificially adding accuracy and precision errors. But of course, the device's own tracking quality and the user's initial accuracy and precision cannot be ignored. Therefore, right after calibration, we first recorded participants' visual status and assessed their initial accuracy and precision. This was done using shoes methods, where users fixate on a series of points, and we measure the resulting eye tracking quality. From this, we observed that with our participants group and the Quest Pro high side, the initial accuracy and precision values indeed showed the expected relationship, with accuracy error being roughly twice as large as precision error. After the experiment, we ran a repeat measure ANOVA with bufferoni correction to analyze completion time, speed, and error rate. First, from the data, we saw that although gaze is not sensitive to distance in selection task, in steering task, the pathways becomes a strong constraint. Users had to keep their navigation more controlled along the path. As a result, they did not rely on quick scans, but showed a strong dependence on time. Second, we observed a very high error rate. Even without external quality error, the error rate was over 50%. This suggests that for gaze-based steering tasks, the path difficulty should be lowered to improve usability. Another important finding is that precision had a greater impact than accuracy. Users can compensate for accuracy errors caused by a fixed offset, but they cannot deal with the jitter in gaze. This means that improving precision should be the main focus for eye tracking optimization. We first tested the original steering law across all conditions. The fit was not very good, with an R-square of 0.79. After we separated accuracy and precision and fitted the model again, the fit improved a lot, reaching R-square equals 0.97. Then, we asked how accuracy and precision actually influence performance. Based on the data turn, we tried 4 regression models: linear, power, logarithmic, and exponential. Both the linear and exponential models worked well, but since the linear model is simpler and still explains the data, we decided it is enough to capture the effects of accuracy and precision on steering time. After understanding the influence of the variables and the characteristic of the eye, we introduced a set of candidate models. First, since gaze is not linear with distance and there are micro scars, we added an exponential term to weaken the distance effect and introduced a constant to limit the usable width. This gave us candidate model 1. Second, from our analysis, accuracy showed a medium effect size on movement time. And since a linear relationship can explain the influence, we propose candidate model 2. Third, precision showed a large effect on movement time. Again, with a linear relationship explaining this, we proposed candidate model 3. We also checked the interaction between accuracy and precision, but it was very small, so we did not build a separate model for it. Finally, by combining both accuracy and precision, we obtained candidate model 4. We then fitted the baseline on all 4 candidate models using nonlinear least squares optimization, testing multiple initial parameter values. The results show that model 4 performs the best, and its AIC and BIC are also significantly lower than other models. To test the reliability of our model, we first ran cross-validation. From the 96 conditions, we randomly selected 72 for training and left the remaining 24 for testing. We repeated this process 100 times, and the model 4 consistently showing the strong robustness. To go further, we conducted another user study with different path parameters, different accuracy and precision on settings, and even different devices like Pico Pro. We also introduced the frame rate as variables to test our model. The results show that at both 30 Hz and 72 Hz, our candidate model 4 still performed significantly better than the baseline, which provide additional evidence of the model's robustness. To show the value of our work, we looked at 3 application scenarios. In VR cascading menus, our model can adjust menu size to match tracking quality. For pop-up notification, users can steer their gaze to dismiss them, with control wise adapted to accuracy and precision. And on the Apple Vision Pro, gaze steering can be used to accept or decline phone cells, will our model help keep performance consistent. From these examples, we draw 3 design recommendations. First, adapt pathwise and learn dynamically based on initial accuracy and precision. Second, only use gaze steering when tracking quality is sufficient. That means accuracy within 1 degree and precision better than half a degree. Third, apply tolerant steering tasks, such as those suggested by Yamanaka, where users are allowed to briefly go outside the path. Taken together, this application and guidelines show how gaze steering can become more robust, adaptive, and user-friendly. Thanks for your attention. I'm happy to take any question.
Yeah, thank you for the talk. Do we have any questions from the audience? We have engaged runners that bring you a microphone.
Hi, thanks for the very interesting work. Really nice. Doug Bowman from Virginia Tech. I guess you maybe started to answer my question on the very last slide with your recommendations, but I was going to ask, just based on this experience, do you think that it's a good idea in general to try to use gaze as an input modality for steering tasks? I mean, I would have said based on the characteristics of eye movements that it wouldn't be my first choice, just because of kind of the non-continuous, saccadic nature of eye movements. So do you think it's still a viable alternative?
Yeah, so like I just mentioned that steering tasks have lots of different types, like walking, driving, and if you are from a starting point to an end point, from a constraint path is steering task. But I think use gaze to navigate a path is very adaptive to use in the user interface, like cascading menus. And we should use like Yamanaka's model, like to tolerate users, like make users, give user more pathwise to improve the usability. Yeah.
Sure. So I guess my question is more like, do you think that we should keep the user interface the same and apply gaze as the input modality, or if we have to use gaze, should we redesign the user interface so it avoids steering tasks?
Sorry, I didn't catch the question.
So you gave the example of like navigating through submenus, right, as a canonical steering task example. If I have to use gaze in my system as an input modality, maybe what I should do, rather than trying to make that steering task as tolerant as possible, maybe I should just redesign the menu system so it doesn't require steering. What do you think about that?
Yeah, yes, you use other input modality is more stable and more efficient. But like Application Pro, we don't use a controller, and we just have the gaze input modality and the hand input modality. So I think use gaze modality in some conditions is okay.
Okay, thanks.
Do we have any more questions? We have still room for one more while we maybe already switch speakers.
Can I start? Hi, everyone. My name is Bo Yuan. I'm from Pacific Computing Lab, University of South Australia. I'm here to present our work focused on task guidance, adaptive AI instruction via gaze and location tracking. So AI has shown great potential for hands-free task guidance, offering context-sensitive instructions that improve efficiency. However, current guidance systems are typically rigid. They present fixed-pace instructions that don't adapt when the user's attention shifts or when distraction occurs. When focus is lost, users often make more efforts and take longer to recover. It can be clearly shown by this recording from one of my participants. So you can see here, we use the alarm as the distraction, and the participants need to deactivate it. And you can see here when she's trying to interact with the interface, she accidentally here tapped to a wrong part, and the timeline jumped to the part that she didn't want. So this is part of our motivation was to address this limitation by making AI guidance focus well. And we ask, how can the adaptive AI systems dynamically respond to users' attention? To do this, we combine gaze tracking, which captures what users are looking at, with location tracking, which provides spatial context. Together, this allows the system to detect when the users lost focus and automatically adjust playback speed or cues, helping them recover attention without manual control. So while the previous AR systems have made progress in improving task efficiency, most of them don't consider what happens when users get distracted or lose focus. So there's a lack of studies examining how the users recover from the task interference, how they regain attention or resume tasks after visual or cognitive disruptions. Second, the roles of gaze and location tracking in recovery remains largely unexplored. Although both have been used in AR guidance, no previous work has systematically compiled how gaze-based or location-based cues help users detect or fix errors after interruptions. Finally, there's a limited understanding of how to combine these cues adaptively. So we ask the question, how can this task guidance system use gaze and location tracking to support users in recovery from distractions or maintaining task efficiency? So the first question is, how do we decide what part of the user need to focus when they operate in the task guidance? So in our observation, the task guidance, when the expert is doing the task guidance, this can be divided into 3 stages. The first one is moving, the second one is scanning, and the third one is operation. And the operation is actually the part that the novice user need to follow or pay attention to. So during the scanning, the user's gaze and head start aligning toward potential task objects they are exploring, and when they reach the face, gaze and hand positions stabilized, showing the full engagement. That's when detect the focus state starts. So this forms the basis of our focused adaptive playback, which I will show next. So this is a short video about how our system works. So the left side is the gaze condition, and the right side is the location condition. So when they move away from the focus aware area, so the playback will adaptively change. And here we show how this behaves under the 2 different modes. So in the gaze-based mode, playback slows down when the user looks away from the target area. And if the gaze leaves the area of interest completely, the playback pauses until focus return. And in the location-based mode, the system monitors the user's physical position. When the user moves outside the target area, playback slows or stops when it returns and it resumes once they return. And here, the third panel shows a marker under the timeline, providing the consistent task progress feedback all across all the conditions. And at the bottom, we summarize the logic. When users are fully engaged, playback runs at 1 time speed, and partially focused will slow it down to 0.5 times. And if the focus is totally lost, the playback is paused. Together, these 2 modes demonstrate how gaze and spatial engagement can drive contextual and adaptive playback. So you are seeing how the system works, and here is what we wanted to test with it. We designed a 2x2 within subjects design with gaze and location tracking on or off. And we explore the 5 key aspects: whether the gaze helps reduce errors and improve recovery, whether the location improves spatial orientation and efficiency, and how the adaptive playback supports recovery after distraction, and whether combining cues leads to better accuracy or overload, and which type of the cues user ultimately prefer. And in this study, the participants perform an assembly-style task while following the AR guidance on the HoloLens 2. The environment was arranged with 6 workstations, and as shown on the top-down map. Each table represented a task location, and the participants started from the central point. And each location, they need to move and place blocks according to the instructions. And the moving area contained 5 source blocks, and the place area had 3 slots for arranging them in a specific pattern. To simulate the real-world distractions, we inserted an interruption task. The participant had to type a prompt word on the keyboard when the alarm appeared before resuming their main assembly task. And the participant need to repeat this process 5 times. So there are total 20 participants involved in the study, and 12 of them didn't have any AR or VR experience before. We evaluate both objective measures, including arrows, recovery time, and interactions, and the subjective measures, including workload, usability, preference, of them to capture the task performance and user experience. So we used the linear mixed effect model to analyze our measurements. We found no significant difference in the completion time among the 4 conditions. This indicates that adaptive playback maintained comparable task duration across all modes, despite pausing and slowing during the loss of focus. And gaze and location guidance significantly reduced the undetected errors, fixed errors, and manual clicks compared to the baseline, while missed were capped by the performance of gaze and location. Both gaze and location improved alarm recovery and reduced workload, while the mix performed worse than a single condition in some cases due to redundancy and cognitive interference. Friedman test was used to evaluate scores of ranking results. This table shows them across the 5 dimensions. Overall, both gaze and location outperformed the baseline in nearly all the measurements. And location consistently scored the best for maintaining focus, reducing workload and physical demand, and the gaze helped users recover faster from the interruptions. In contrast, the baseline performed worse across all the metrics, and the mixed condition offer non-clear advantages, sometimes even adding extra cognitive load. Together, these results confirm that the gazing and location guidance provides a clear and less demanding user experience than combining multiple ones. Here are some of the key findings of our paper. So the gaze effectively reduced errors and supported faster recovery after interruptions. And the location provides stable spatial orientation and help lower perceived workload. And however, when the gaze and location were combined in the mix, the benefits didn't add up. Instead, they sometimes cause redundancy and cognitive overload, slowing the recovery, especially when the users try to re-engage after disturb. So this suggested that the simultaneous multi-cues can overwhelm attention and should instead be coordinated and alternated dynamically. Finally, the adaptive playback mechanism, which automatically slowed or paused playback based on their focus, was highly effective, and the participants rarely noticed it, yet it delivers smoother task flow, fewer manual interactions, and a stronger immersion, showing the promise as a generalized method for adaptive AR guidance system. So there are the several, we have the 2 key design in insights and a set of guidelines. The first, gaze-based guidance works best for the fine-grained and critical tasks, such as the inspection or surgery. It supports quick recovery after interruptions and reduce manual control efforts. Meanwhile, location is more suitable for navigation or specially distributed tasks like assembly or training, where orientation and consistency matter more. And in terms of the design guidelines, we found that using multiple cue simulators can cause cognitive overload, so systems should avoid uncoordinated multi-cue feedback. Finally, adaptive playback, which automatically pauses or slows when focus is lost, proved to be an effective tool to support smooth attention recovery. So of course, our study has a few key limitations. The first, the HoloLens 2 hardware introduced some constraints, such as latency and a limited field of view, which may have influenced user perception. And second, this work was conducted in a controlled lab setting, so ecological validity is still limited. And finally, the scope focused only on gaze and location without exploring other modalities. Looking forward, we plan to develop a dynamic cue switching mechanism that intelligently alternate between the gaze and the location based on users' context. And we also trying to explore multimodal adaptive cues such as gesture, voice, or biosignals, and aim for real-world deployment in training and industrial environment. So wrap up, we develop an adaptive AR task guidance system that integrates both gaze and location tracking to adjust playback in real time based on the user's focus state. And our results show clear advantages for each the guidance, gaze reduce undetected errors and help user recover quickly, while the location improves spatial orientation and lower the workload. However, when both were combined in the mixed condition, we saw diminishing returns rather than improvement. The overlap between queues occasionally creates the cognitive overload, slowing the recovery and reducing efficiency. Finally, the playback mechanism, which automatically pauses or slows the playback when the focus is lost, proved highly efficient. So it supported smooth recovery and reduced manual control efforts. And that's all for my presentation. Thank you for listening, and I'm happy to answer any questions.
Thank you very much. Do we have any questions? Okay, I have one question while you all have a second to think of your questions. You have these thresholds for the location-based feedback, so when the video paused or slowed down.
Yes, yes.
What's the best way to decide on these thresholds if we would use this technique for another scenario or so?
Oh, in my situation, in my study, so as long as we are the assembling task, so I think when I decided how the threshold of the location or the gaze, so I'm using the basically the first for the gaze is about the field of view of the equipment, which is HoloLens 2, and for the location, I'm using the distance of my arm. So basically, when you're trying to assemble something, so your distance between the your focus area or your workstation must be within 1 arm distance. So I'm using that as a threshold. And I think if you want to expand to any other situations, so I think that's similar. As long as you are using your hand to manipulate with devices, so I think the threshold is still useful. Yeah.
Thank you. Any more questions? That seems, yes, there is one. Thank you.
Thank you. Just one question. Great presentation, by the way. Thank you. You mentioned, if I remember correctly, that you couldn't find any significant difference between the completion of the different tasks. I was just wondering if you actually had any insight about that, because that's surprising to me. I feel like location-based or gaze-based would be much better.
You mean the completion time?
Yeah, that's right. Yeah.
Oh yes. So that surprised me as well, because I think probably base should be the shortest one. But I think that because, as I mentioned before, because over half of my participants didn't have any previous AR or XR experience, and I observed that during when I looked the recording of their study period, I can find out they make a lot of mistakes when they're trying to interact with the AI interfaces. At first, I doubt is that because I didn't give them enough training, but I found out that's not, because if you ask a guy who didn't have any XR experience to kind of like interact with an interface that's high in the sky and didn't have any feedback, I think the experience itself is quite difficult to understand in a short period. So I think that's why the completion time didn't have a significant difference, because when the participant trying to interact with the timeline, when they get disturbed, so they make mistakes time to time. So sometimes they realize, oh, I make a mistake here, and I'm trying to reverse back. But some of them actually didn't realize that. And after they deal with the disturb, they come back, they find out, wait, why the playback didn't match what I just operated. So they spend even more time to kind of figure out where they were and how they could go back. So I think that's the main reason why the completion time didn't have a significant difference. Yeah.
Yeah, right. That makes sense. Thank you.
Thank you very much for the talk.
Thank you.
Thank you. Yeah, I wanted to talk about a gaze-controlled wheelchair. And we already heard in our first presentation today that gaze is an established steering system for tasks like navigation. And to maybe answer a question that wasn't directed to me, a wheelchair like this would obviously, the end users would be users with severe motor impairments. So you kind of have to use gaze under these circumstances. Yeah, and while gaze is obviously a great cursor because it is a really precise cursor, you don't have an intuitive selection method that comes with gaze. So you obviously look at what you want to do, but you also look at other things for other purposes, as gaze is a multi-purpose system. And that is basically the Midas touch problem. You don't want to select everything, just as King Midas doesn't want everything he touches to turn into gold. And when you apply that to locomotion, there are two types of gaze movements. The gaze movements that are indicative of locomotor intention, and there's an extensive body of literature that establishes the tight relationship between gaze and locomotion targets. And obviously every other gaze movements that you do during locomotion, for example, to gather information or to search for something, or maybe because a tree is beautiful. And most gaze-steered wheelchairs have fallen into two categories. Either you can ignore this problem, this works, you can still steer the wheelchair. Basically, everywhere you look is where you go, is then the idea. But this is really annoying because when you look at something else, the wheelchair also steers in that direction. And the other possibility is to add a selection method on top of that. So the most common one is dwell time. So we have a dwell time activation, but this makes everything really slow. So it's also an imperfect system. Our proposal is to phrase the question as a binary classification problem and tackle the Midas touch problem very directly. So you have these two types of gaze movements, and you classify them in a binary way using a model that you train to do that. So to have locomotion intention and no locomotion intention. So in a system, you would feed the eye tracking data into an intention decoder model, and then you would only use those gaze movements that the model declared as locomotion intention for steering the wheelchair and changing the angular velocity. And the problem that remains is that the users lose a lot of agency when you do that, because there's like a black box model that decides for them whenever it's applied. So to give a little bit more trust into the system and to foster like bidirectional communication, you give the users feedback. So an explicit feedback signal that shows them what the model thinks, what the user is doing. And then the user potentially can react to that, especially if there's something wrong. We used a three-step process. So first of all, we developed a model to do that binary classification task. Second, we did an evaluation task that was done in virtual reality under controlled circumstances. And third, we implemented that in an actual physical wheelchair to show that this really works. So let's start with the model development. We used joystick data for that, as it's closer to wheelchair navigation than physical walking. And we use multiple data sets of multiple tasks where users steer through virtual environments using a joystick, and we had their gaze recorded. We then took the history of eye and locomotor data, specifically 2 seconds of that, and fed that into the model. And we automatically computed our labels with the question, will the users look where they go? So at each and every time point, we looked into the future. We could do that because we had already all the data. And then we asked, at a later point, will the user be there? Or will he or she not be there? And then we would know if the gaze at that specific time point would be indicative of locomotor intention or not. The best performing model for that binary classification task was a transformer model. However, you also get a really good prediction with much simpler models, but we still opted for that because it gave us the best results. We also played around a little bit with the features. We tried to add EEG data, which didn't really work in our case. And actually, if you only use the history of eye tracking data, that also gives you a really good prediction. However, our final model uses positional data and the history of eye tracking data, and uses a transformer architecture. We then conducted a virtual reality evaluation experiment with 3 conditions. The intention decoder for steering, this is our model, and you were steering with our model. The intention decoder, but you would also get a feedback signal and a direct action baseline. A direct action baseline here just means you ignore the Midas touch problem, you turn every type of gaze movements into a directional change, and yeah, it's basically your locus where you go system. I want to specifically show you a video of this second condition, the intention decoder with feedback, because then you understand everything else as well. And before I start the video, just to explain it, you had a double task here. So you had to follow that black path, that's a navigation task, while at the same time you had to do a visual search task. You were looking for these gray cylindrical objects. Most of them had 2 blue lines, but few of them had 3 blue lines, and you would have to count those with 3 blue lines. The details are not relevant, it's just a counting task, basically. And you had this double task to force users to look somewhere else, which is also something we do under natural conditions. You also see that blue circle in the middle. This is the gaze position of the user. The users weren't obviously seeing this. I just added it for the video. But the users were seeing that huge pink circle that you see there, and this is the feedback signal. Whenever you're seeing that pink circle, the system thinks this is locomotion intention, and whenever that pink circle is absent, the system thinks this is not locomotion intention. This looks pretty intrusive, but it was actually visible in the periphery, so when you were in the experiment, it wasn't as intrusive. So this is the user steering around, just using his or her eye movements. The blue ball indicates the gaze position, and you see sometimes the pink circle is visible, sometimes not. So this, for example, is an instant where it's visible, and then this is movement intention, and then the angular velocity of that virtual wheelchair is adjusted. This would be an instance where it's not visible. That means the system thinks this is not locomotion intention. You're looking at that gray cylinder. And then the virtual wheelchair doesn't steer in that direction. So this way users can look away, for example, to count. Our hypothesis, or our main hypothesis, was that this intention decoder enables smoother steering. So the idea is if you have this direct action baseline control system, you can solve the task, but it's really annoying because whenever you look at a cylinder to the left, you steer to the left, and then you have a steering adjustment to the right because you have to go back to the path, and it's all of these back and forth steering adjustments which are really annoying. Whereas if you use our intention decoder, you don't have them. When we looked at the distance to the path, this is the baseline in yellow, then our intention decoder in blue, and the one with feedback in pink. Our intention decoder was a little bit closer to the path, or users were closer to the path using that, but the difference is tiny. However, when you look at the orientation deviation, this is the difference between the orientation of the black path, which would be optimal, and the orientation of the user, you have much bigger and actually a significant difference between our intention decoder in both conditions and the baseline. Lastly, we looked at smoothness. This is the inverse of the amount of angular change. And here you see a quite drastic difference between our intention decoder and the direct action baseline. So we confirm this hypothesis that this actually enables smoother steering. Yeah, so what about the difference between displaying feedback or not displaying feedback? First of all, we found that with the feedback, the counting errors are much lower. This is a bit of a spurious finding, but maybe we didn't have a strong prior hypothesis for stuff like this. And we also asked the user about to rate the performance, agency, and trust. Again, in each of these categories, the intention decoder with feedback outperformed the intention decoder without feedback. Actually, in the performance rating, it even outperformed the baseline. However, the variances are quite large here. Okay. To conclude this, I wanted to show you the wheelchair demonstration that we did, and it's similar to the VR video that you just saw. This time we implemented the system in a physical wheelchair, and this was done with the HoloLens, an augmented reality device now. Whenever you see the green circle, or the user is seeing the green circle on the HoloLens, this means this is movement intention, and whenever the green circle is absent, this is not movement intention. So same idea, but pink turned into green. don't get confused by the blue circle. This is the start and stop button that you can activate with a dwell time threshold. Okay, so we start really slow. This is the video of the wheelchair, and you can see I can look out of the window and the wheelchair doesn't go in that direction. And that's really nice because I'm steering along a very narrow path here. Obviously I have to look to the path a little bit, but I can also look out of the window and the system doesn't direct me in that direction. And that's the beauty of the system. So it seems like a lot of this is just looking down, but actually there are other cues than looking down. For example, having your head and eyes aligned is also an indicator of intention decoding to the system. So on a video like this, it looks really annoying having this green circle, but keep in mind this is the user's gaze, so you don't see it that way when you're using the HoloLens, as we see it in a video like this. It's actually a little bit less annoying when you're doing it. So this was the trail time start button, and the goal here is to go to another room. Yeah, and you can start the system, you can stop the system. It also has a little bit of speed control by looking upwards and downwards. And that's basically it. Yeah, so to conclude, we developed this locomotion intention decoder based on phrasing the Midas touch problem as a binary classification task, and our system actually enables smoother steering. So I think my time is over. So thank you for your attention, and do you have any questions?
Thank you very much. Do we have any questions? Many questions. Excellent.
Thank you for the talk. I have a question about when a user might want to be looking and moving at the same time. So for example, if they're following someone, they need to follow someone, and they're looking at the person in front of them instead of the path. Do you have any ideas about how you might handle those types of edge cases or situations?
So I can't give a perfect answer to how the system would react in specific situations because it's a black box model at its core. So if you were to follow a user in a way that would be straight in front of you and you have your head and eyes aligned, if you, for example, follow a person with your gaze, then I guess the system would predict this might be locomotion intention. Whereas if you do it in a way where your eyes and head are not aligned, I think it might say it's not locomotion intention.
Okay, thank you.
But that's just a guess.
There is one more question in the center there. Yeah, thank you. Microphones come from the other side, probably.
Thank you for the talk. Pavel Manachov from Lancaster University. Somewhat following up on the previous question, I was wondering whether in your future work you are planning on including more complex, ecologically valid scenarios, because for instance, if I understand correctly, there was no obstacles in the training experiment, the first one, right? But in real life, there may be people walking around, there are a lot of obstacles which I need to track and accordingly correct my trajectory. So what are your thoughts on how to improve the system to include all this?
Great question. We actually had like a course with a tiny obstacle. This is in the paper, but I didn't like with a wheelchair. Right now we already have a data collection with like a more complex obstacle course where users had to avoid these and do stuff at the same time. But this was after I submitted my paper.
Thank you.
Yeah, let's thank our speaker again.
Hello everyone, I'm Maria Gorlatova, as introduced. I am one of the authors of this paper. The lead author unfortunately could not be here today. He's very sorry about that. He is very eager to engage with you on Discord or over email. His email is on the screen. So this work is about situational awareness in augmented reality. And one of the exciting use cases for augmented reality is being able to present additional information to the users to improve their situational awareness. One of the examples of such use cases on the screen, and many others are possible. But it is worth noting that giving users additional information does not necessarily mean that their situational awareness is improved. Situational awareness is generally understood to have 3 levels that are shown on the screen here: perception, comprehension, and projection. And there is really no guarantee that giving users extra information will improve the comprehension or projection. In fact, a number of works have demonstrated that augmented reality can even decrease user situational awareness if the users are paying too much attention to virtual stimuli and are ignoring the broader context of the task that they're supposed to be performing. So in this work, we are asking ourselves, can we tell if situational awareness has been impaired in an AR scenario? We have all those wonderful eye trackers that are built into many of the AR headsets. Can we use those capabilities to see that user situational awareness may have been impaired? For the study, we are using a setup of AR-guided CPR, specifically AR-guided chest compressions in CPR. And chest compressions are a very interesting application for AR guidance. To be effective, they have to be done at a certain rate and at a certain level of depth. At the same time, when somebody is doing chest compressions in CPR, they cannot keep focusing on chest compressions alone. They have to keep monitoring the overall state of the patient. If the patient starts to bleed, that has to be attended to before compressions should continue. And if a patient vomits, then their airway might be blocked, and the airway needs to be cleared before chest compression should be resuming. So this is the setup that we are exploring in this work. And in context of this work, we are creating an AR app for CPR and are creating a study with realistic incidents that allow us to study situational awareness. We conduct a 30-participant user study where we identify situational awareness to be negatively correlated with the focus on virtual content. And we build an ML model that allows us to predict situational awareness with a very good accuracy that outperforms a number of baselines. The AR app we have designed is shown on the screen here. We implemented it on the Magic Leap 2. It provides users with the guidance about the rate and the depth of chest compressions. It has been designed in collaboration with healthcare professionals and has been rated as helpful by over 95% of our user study participants. At the same time, in addition to the app, we also designed a setup that allows us to simulate incidents that are happening while the users are performing chest compressions. In the CPR dummy, the chest cavity is hollow. And we use this opportunity to hide a number of hardware pieces there that we need to create incidents that emulate emergencies happening to the dummy. The hardware is shown on the screen here. And one of the incidents that we are creating is simulated bleeding. You will see it in a second. Okay, so here the dummy starts to bleed, and the user is attending to that before they are resuming the chest compressions. And this is a case of implementation of vomiting. You will see it in a second as well. So here the user is attending to that. So using the setup, we conducted a study with 30 users, and the users were instructed, as is shown on the screen, to perform CPR while simultaneously monitoring the overall status of the patient and use their own judgment to decide what to do if an unexpected incident has happened. Medical supplies were provided. You see the setup on the screen here, but the participants were not told that they have to use them. Study procedure consisted of questionnaires, cognitive tests, a practice trial, and then the bleeding and vomiting trials in random order. The trials were continued until the incident has been emulated. And with that emulated incident, we stopped the trials after the participant responded to it, or if the participant didn't, 5 seconds after the incident has happened. How we coded situational awareness is shown on the screen here. We base it on our observations as well as on users' answers to questions that correspond to the 3 levels of situational awareness. Additional details on that are in the paper. And overall, we have seen a number of cases of impaired situational awareness with this setup. Out of 60 total incidents, 24 ended up being labeled as poor situational awareness. We continuously collected eye gaze of our participants in this case. And we performed analysis of what gaze looked like in windows of several seconds before the incidents occurred. We looked at metrics related to saccades and metrics related to gaze targets. And overall, some of our results are shown on the screen here. They show different gaze metrics for the 3 different time windows before an incident for users that have poor and good situational awareness. And what you see here, and what we have observed in the study, is that without any reasonable doubt, across many time windows, across many metrics, people who have good situational awareness and people who have poor situational awareness have very different visual behavior. As is written here, the users with good situational awareness effectively have broader and faster visual perception. They pay less attention to virtual content overall. They do not over-engage with it, as users with poor situational awareness do. And we have observed this across many metrics that we have seen and across many different time windows as well. So those findings are very consistent in the study. Having seen that users with poor situational awareness look at the scene differently, we then build a machine learning approach to be able to classify behavior as visual behavior as corresponding to poor situational awareness. We again look at those small short time windows before an incident. And in this case, we model users' visual attention as graphs that we represent fixations as nodes in a graph, and we represent relationships between fixations as edges on the graph. A temporal edge corresponds to 2 fixations happening in succession, while a spatial edge corresponds to fixations happening in close geometrical proximity. The nodes and edges features are shown on the screen here, and additional details of this admittedly fairly complex model are in the paper. Using this graph model, we've relied on an edge pooling architecture to create a classifier. In this architecture, the edges that have certain properties are pooled, and then the classifier acts on both the original and the pooled versions of the graph to make predictions. The actual task here that we train this model on and deploy it on is predicting that user situational awareness is poor based on 21 seconds of gaze data before an incident. Some of our results are shown on the screen here. More results are in the paper. Our model that we call fixed graph pool significantly outperforms a range of baselines of different complexities. And we also conduct an ablation study that demonstrates the importance of some of the choices that we made in this modeling and in this classifier design. The study has some limitations. This is one UI design. It has been built in collaboration with healthcare professionals, but it does impose high visual load on some participants potentially. You've heard the drum beat music that we use in this app. This is considered highly beneficial for CPR as it helps pace compressions. But at the same time, it is entirely possible that this drove some users to over-engage with the content. Model generalizability is something that we actively explore. We are currently testing applicability of our model to other gaze-based tasks. And we also noticed something very curious in the data, that we have asked our participants to report on their attention shifting ability using a standardized attention control questionnaire. And what we have seen here is that people who believe themselves to be good at attention shifting actually do worse on situational awareness. And they do worse in terms of the label situational awareness and associated gaze metrics both. There are parallels to this finding in literature on multitasking, that people who believe themselves to be better in multitasking actually tend to perform slightly worse on tests that require multitasking abilities. And this is a finding that we will keep following up on, as this may be one of the easily measurable and easily obtainable measures that correspond to the heterogeneity in how users respond to visual content in AR. So overall, in this work, in a study of AR aided CPR, we have demonstrated that certain visual metrics correlate with poor situational awareness, that effectively people with poor situational awareness excessively focus on virtual content. And we have built a model that allows predicting situational awareness via eye tracking data that outperforms multiple baselines. This is an active ongoing project. The setup is ready. The data collection pipeline is in place. We are very interested in collaborating with other people who are examining situational awareness as well as other attentional compromises in AR. So please talk to us if you're interested in collaborating. We are actively continuing on this work. I want to thank our sponsors. I want to thank the healthcare professionals that helped us build the app and design the study, as well as our partners who specialize in attention, who are helping us interpret some of the results. And I want to guide you to the code repo that we have made available. And thank you.
Thank you very much. There are already questions in the audience.
Thank you for the talk, Pavel Monachov, Lancaster University. I was wondering whether the model is also applicable to dynamic situations, because if I understand correctly, the situation you just described, it's the person hovering above the patient, right? And the fixations in this particular case would be kind of stable. The head relative to me is here, and then the bleeding is over there, and fixations are kind of, they don't move in regarding to me, but I was curious about situations where the person is moving, so the targets are moving relative to me within the visual field. Would this model be applicable to those situations?
Yes, that is an excellent question. So overall, we have built this to be it is a 3D gaze tracking task. It is fully adapted to 3D environment, that if your gazes are landing elsewhere and your head is shifting slightly, that is okay. If your environment is highly dynamic, probably you would need to make some adaptations. But we have done some other work on gaze modeling with graphs that was 2D, but this is 3D. This is, yeah.
Thanks so much.
Do we have any more questions?
Thanks for the talk. And my question is that basically you are using subjective questionnaire for getting the score of situational awareness. And I think we could use some data analysis or computation for getting this kind of measure. How do you think about that?
You mean for attention, for users' attention abilities, or for the situational awareness scores?
For the level of situational awareness.
So our situational awareness, so we follow a fairly standard approach where we are. So first of all, we observe people.
Yes.
That's the first thing we do. And what we are able to tell from observations is whether someone has missed a stimulus. So
yes.
that's very clear. We look at them and we see it.
Okay.
Then past that, we use this approach where we try things like comprehension and decision making. They're hard to have an objective measure for.
So yes, it's difficult. But for example, by the use of tracking data, we could have this kind of metrics or something like that. Yes.
So what we try to do here is that we try to observe people. We try to guess what they think based on the observations, and then we also ask them questions.
Okay.
So yes, there is some room for. We played with labeling a little bit. There is more room for experimenting with it. Yes.
Okay, thank you.
Excellent, great. That brings us to the end of our session. Let's thank Maria again.